Now we'll load the sample into the chamber with standard procedures. The one difference is we flip the stage setting from A to C so that we can measure the current of the beam as it comes through. Our SEM is equipped with the Navity NPGS nanometer pattern generation system. That includes the beam blanker and also a CPU equipped with a couple pieces of software. One of those software programs is DesignCAD, and that's the program we use to actually define the pattern that we're going to generate. The second piece of software is the actual NPGS run file software. That controls the exposure conditions that the microscope uses to generate that pattern with good fidelity. When we execute the run file, the NPGS computer is going to position the beam in the column using the scan coils on the SEM. This is the external beam blanker, which is also going to block the beam when it goes across parts of the pattern that are not exposed. Different EBL machines have a wide variety of performance. With this system, we routinely write lines of about 50 nanometers in width. Dedicated E-beam writers can also write fine lines of about 7 nanometers in width, and they have a lot of other advantages besides. After I've launched the NPGS menu, there's a link to the DesignCAD program. So I can open DesignCAD from this button. And DesignCAD has a lot of tools for making virtually any pattern you could want. Most of the useful tools you'll find under the NPGS tab. The one that I'll show you is the most common one that we use is the dot array function. So if I pick dot array, it gives me a lot of instructions here on exactly what it wants to do, but I'm going to read hit the 0 to create the dots as filled circles, because I want an array of dots that aren't simply outlines but are whole patterns. So I type 0, the center of the array, OK, diameter of the dots, for example, we'll say 0.2 micron. That's 200 nanometer in diameter. Number of columns, we can say 100 for a round number. And the distance between columns, we'll say 0.4 micron, 400 nanometers. And then for rows, we'll use identical spacing. DesignCAD then generates an array, 100 columns by 100 rows, composed of 200 nanometer dots that'll be filled in by the E-beam, spaced 200 nanometers from one edge to the next. With that file made, I'm going to set the center of the array as the origin. So I select max mag. The pattern area is 40 micron by 40 micron, which shouldn't take too long by EBL. My estimate is the right time for this pattern would be about 10 minutes. The microscope magnification we need is about 5,500, and then I'll save that file and exit DesignCAD. The second piece of software in NPGS is the run file programs. I'm going to open Run File Editor through this button, and it generates a blank run file for me. There's one entity listed here, and that entity is a pattern. You see under pattern name it's blank. If I double click this field, it opens a menu. I can insert any pattern into this run file that I choose. For our demonstration today, there's a file called hex tries that I'd like to write. When I load hex tries into the run file, it then brings up a new list of options. And these are the different writing conditions that I can control on the SEM. This pattern is only one layer. The origin is 0, 0. The magnification that I found from CAD for the last pattern was 5,000. For the current pattern, because it's larger, the magnification needs to be 1,000. The frequency of exposures horizontally is the center-to-center distance. Those will be 20 nanometers apart. The line spacing is the frequency of exposures vertically. I'm going to set that to also be 20 nanometers. The configuration parameter is the same as the spot size on the SEM. And for the finest features, we want to use a spot size of 1 because it has the lowest current. And in the measured beam current field that comes next, it lists the units here as picoamps. And when I measured the picoamps earlier, I found that it was at about 13.9. The last option here, it says multiple pass mode, disable. This is standard for our system. The dwell color with the unit of microseconds is 261 microseconds. This is calculated from the measured beam current and the line dose that I want to expose my resist. In my experience, a resist of this thickness and a pattern of this size will need a line dose of about 0.7 nanocoulombs per centimeter. So if I change the line dose here, you see that the software automatically updates the dwell color above. And then finally I save this run file. Now the run file is complete. We've loaded all of the microscope exposure conditions and we've loaded the pattern. So the computer has all the instructions it needs to reproduce this sample pattern hex tries by writing that pattern out on our chip.